Hello and welcome to this lecture. In this lecture, we're going to look at this exponential function. We've been looking at defining functions through power series, and this exponential function is one such function that one can define using a power series. And like I mentioned, it's got innumerable applications everywhere. So let's get started. Here's the definition. The definition itself is very simple. We've seen it sort of before. Exponential x, it's denoted exp of x in some cases. This function is evaluated at x using this power series 1 plus x squared by 2 factorial plus x cubed by 3 factorial plus dot 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 for any real number x. This is the series summation x bar n by n factorial, n going from 0 to infinity. And we have seen that this has a radius of convergence of infinity, which means it converges for every x, and that's why this is well defined for x in the real numbers. A quick couple of checks. If you put x equals 0, you get 1. Okay, so this function evaluated at 0 gives you 1. Okay, easy enough. Okay, and if you evaluate it at 1, you will get something, right? It will be a convergent series 1 plus 1 plus 1 by 2 factorial plus 1 by 3 factorial, so on. That number is usually denoted e. Okay, we'll have more to say about this e later on. For now, this is just a definition. Okay, so the exponential function evaluated at 1 gives you e. Okay, so let's see what properties it has. The first property we have already seen is this function, if you differentiate, you get the same function again. And you can do this for every x in R. The derivative exists, the function is continuous. We've seen all this before. In fact, you can keep on repeating this derivative over and over again. So this function is really smooth. It belongs to these functions which can be differentiated forever, right? You can keep on differentiating them. So it's a very smooth function. And the nice thing is every derivative is itself. Okay, so it's very powerful and a strong property that only special functions can have, isn't it? The other functions don't really share such nice properties. Okay, here is the next property, which is very counterintuitive. Okay, so this series 1 plus x squared by 2 factorial x cubed by 3 factorial, it looks really long, and there are powers involved, x squared, x cubed, etc. If you put x plus y instead of x, okay, so what is the meaning of putting x plus y instead of x? If you put x plus y instead of x, as in you do exp of x plus y, that will be 1 plus x plus y by 1 factorial, x plus y whole squared by 2 factorial, plus so on. Okay, turns out this is going to be equal to the exponential function evaluated at x multiplied by the exponential function divided by y. So here we did addition and then we plugged in the exponential function. You got this, and this is going to be equal to this. And what is exponential function at x? X by 1 factorial, x squared by 2 factorial, plus x cubed by 3 factorial, plus so on, multiplied by 1 plus y by 1 factorial, y squared by 2 factorial, plus y cubed by 3 factorial, so on. So here, how do you multiply series? We have not formally seen all these things, but let's say the regular polynomial type multiplication works, let's say. Okay, so that's actually true, you can prove it. But if you multiply like that, it's not at all clear how this x plus y is going to show up here, right? Isn't it? So you notice here 1 plus x, you only have x, and it's not very clear that x plus y is going to show up. Maybe if you see the sums and group them together, you may notice something, but still this needs to be proved. It's not an obvious result. It's a very non-trivial and very important result of this exponential function. This is one of the reasons why this function is called exponential. If you put in the sum of two things as the argument, it is the same as using the individual arguments and multiplying them together. Okay, very counterintuitive, right? Addition is sort of becoming like multiplication. Okay, addition of the argument is becoming multiplication of the function value. Very powerful result. Okay, so I'm going to write a proof for this. It's a quick proof. I won't spend too much time going over the proof. It involves some algebraic manipulations and properties of rearrangement of series, etc. Here's the proof, and it starts with the starting point that I had, right? So exponential exp of x times exp of y. Maybe I should take one of these things. Okay, so you have exp of x times exp of y. This is exp of x, right? Summation I've used a dummy variable r. In these kind of summation tricks, you will see that you have to use two dummy variables. You can't use the same variable, right? Because this is going in one sum, this is going in another sum. You are multiplying this with y power s by s factorial. It turns out by a rearrangement of terms, this a comes from a rearrangement of terms, you can show that this sum is equal to this sum. Okay, I'll just give you one little argument for why this should be true. So you're looking at summation over r equals 0 to infinity x power r by r factorial multiplied by summation s equals 0 to infinity x power s by y power s by s factorial, right? So this is what we're looking at. The first thing you should realize, again, these things are a little bit counterintuitive. You can take this term inside this term in the summation, pull the summation out. So you can have r equals 0 to infinity, s equals 0 to infinity, right? So for every term I'm multiplying by this, so I can pull this in. So all these need some proving for infinite series, right? So we've not proved these things, this rearrangement of terms, but let's say that's true. Okay, so like I said, this strictly needs proof, but all these things are true. Okay, it can be proven. We're not taking the effort to prove it. Okay, so just visualize this in a 2D grid. Okay, so this is very interesting. So this is like the r axis, r equals 0, 1, 2. So this visualization will help you a lot. 4, so on. Right? It keeps on going 0, 1, 2, 3. Likewise, on this side, let me have s equals. So maybe I should start with like s equals 0, and then I have s equals 1, so on, right? So this is like the xy axis. Let me not say s equals 2, 3, so on. Okay, it keeps on going. So this point will be 1, 1, this point will be 2, 1, this point will be 3, 1, right? So every point here corresponds to one particular value of r and s. Okay, so this is the r, s grid. Okay, so you can make one a bunch of dots here. These things have various names. In Tamil Nadu, this is used for drawing columns. I don't know if you're a fan of making a column. So we're not going to do that here, but anyway, nevertheless. So let's have this with us. So this is a grid, then you can keep drawing this. This grid goes on forever, right? So that's the important thing. Now what happens in this summation is, you first fix r, right? One r value gets fixed here, and then you go over s. So if in the first outer summation, which I'm going to show in blue, I go in this direction, okay, this direction, and go all the way and then come back here and then go in this direction again, right? So for r equal to 0, I do s equals 0, 1, 2, 3, so on, right? That's how this loop goes. So you can think of it as a program. You first do the r loop outer and then s loop inner, right? So that's sort of like how you can think about it. So s keeps on increasing and then it comes back once it's done to r equals 1, and then s again increases and then it will come back again and then you'll go back like this. So this way you cover all the dots in column wise. You first go up the first column and go to the second column like that. It turns out you can also cover all the dots diagonally, right? I can start with this diagonal, okay, and then I can go here, and then I can go here, I can go here. Now you might say I'm drawing a column, right? Anyway, so it's not exactly a column. This column, people don't go through the points anyway. So you can do this also. Okay, so let me see how far I can push it. So I can go here diagonally, and then again here diagonally. So this way also I cover the entire grid, right? Convince yourself that this is also a very valid way of covering the entire grid, right? So you can also do it in any other way. So how does that work, right? So that works with the other summation. Okay, so let me just go back to my slide here. This summation is covering diagonally, this summation is covering column wise. Okay, so that's the difference here. So you see n equals 0 to infinity, n denotes the diagonal. In every diagonal, if you see in every diagonal, in this diagonal r plus s equals 0. In this diagonal, r plus s equals 1. In this diagonal, r plus s equals 2, and so on. Okay. So, diagonals correspond to r plus s being something. So, this n is nothing but r plus s. N is going from 0 to infinity. For every r plus s, the internal variable r or s, one of those guys, can go from 0 to n. Okay. So, that's how it works, no? So, in every here r plus s is 1, here r is 0, here r is 1. Okay. So, this point corresponds to r0 and this point corresponds to r1, okay, like that. So, you can see 0, 1, 2, etc. So, r goes from 0 to n, 0 to n, and then s will be the other way around. Okay. So, r plus s has to be n. So, you see here r became x bar k by k factorial, k is r, and then s became n minus r, n minus k by n minus k factorial. Okay. So, think about why this is true. These two are true. Once this is true, you can do other things, like for instance, what I have done here, nothing much. I have divided by n factorial, multiplied by n factorial. I have not done any other manipulation here. And this expression is a very familiar expression for those who know binomial expansion. Also, this is something we have not seen in this class. I will urge you to look at it if you want to. So, this, it turns out, is the same as x plus y power n. Okay. Leave out this 1 by n factorial, which came from somewhere. This summation is the same as x plus y whole power n. Once you see that this is the same as exp of x plus y. Okay. I know I did not do every step in detail. The point of this proof is to show that the exponential function satisfies this wonderful, powerful addition formula. Exp of x plus y is exp of x times exp of y. And the proof comes from rearrangement of terms after multiplying two series. We have not proven any of those strictly for the series, slightly more technical and advanced. And then you observe doing this, after you do this rearrangement, you observe this binomial expansion showing up here, and you're done. Okay, wonderful, wonderful property. Okay, so this property is very crucial. You will see it defines the exponential function in a wonderful way. We'll see that soon enough. Let's see a few more properties for the same exponential function. The first is, for x positive, exp of x is greater than 0. This is very easy to prove, right? For every term here, if x is positive, every term here is positive, and I'm adding all the positive things together, I can never get anything negative. Okay, so exp of x is greater than 0 for x greater than 0. Okay, so this is how the function behaves. We are looking at the behavior of the function. Exp of x tends to infinity as x tends to infinity. That's also not too difficult to see, because it's greater than x, or greater than x squared by 2 or whatever. So, as x tends to infinity, these things blow up and they go off to infinity. Of course, for every x, it converges to some value. Okay, don't think it diverges for any particular x. But as becomes larger and larger and larger, that converging value goes off to infinity. Okay, so that's the way to think of this function, this statement. Another thing is, if y is greater than x, then exp of y is greater than exp of x. Okay, that's also very easy to show for both x and y positive. Okay, why? Because instead of x, you will have y here. If y is greater than x, you can see term by term, this exp of y will be greater than exp of x. Okay, so exp of y will be greater than exp of x. Is it okay? Every term of the summation of exp of y is greater than the corresponding term of exp of x. So, when you add it all up, this will become greater than this. Okay. So, these are also easy to prove. I am not showing the proof here, but the argument is very easy. For positive case, this is very, very powerful statement. Okay. So, exp of x is a smooth function. It satisfies the addition formula. On top of it, it's positive for positive x. It tends to infinity as x tends to infinity, and then it is increasing. So, this property is basically the function is increasing monotonically for x greater than 0. That's what this is showing, right? For y greater than x, the function is also greater. Okay, that's the first property, sign and the order. The next property, I'm going to call it the inverse property, and the inverse basically satisfies this. Exp of x, exp of minus x is equal to 1. Okay, so basically this means, so how to prove it? First of all, proving it is very, very easy. Put y equals minus x in the addition formula, right? Let's go back and look at the addition formula. If I put y equals minus x, I'm going to get exp of 0 here is exp of x times exp of minus x. What is exp of 0? That is 1. Okay. So, clearly this is an easy thing to prove. Okay. So, another way to write this down, if you're thinking about what it means, is exp of minus x is 1 by exp of x. Okay, this is another way of thinking about it. So, the negative value, if you evaluate exp, you get 1 by exp of x. So, this is also a very interesting formula. So, what is exp of minus x? It is 1 minus x by 1 factorial plus x squared by 2 factorial. How do I get plus here instead of being minus? Because it is x squared, right? So, it becomes positive. So, you are squaring it 3 factorial plus so on. This is equal to 1 by 1 plus x by 1 factorial plus x squared by 2 factorial plus so on. Okay. So, these things are not at all obvious. I mean, unless you prove these things, it is not at all clear that this series is 1 by this series. Okay. So, it is like a multiplicative inverse property. That is why I call it inverse function. Now, what this means is all these properties that we had on sign and order, using this inverse relationship, I can push it to the negative x also. It is very easy. So, you see here, exp of minus x is greater than 0 for x greater than 0. So, even if x is negative, the exponential function is positive. Okay, wonderful, isn't it? So, this is a very important relationship, and that comes from this. How do you prove it? If you put x as any positive number, you have exp of minus x being 1 by exp of x. exp of x is positive, so 1 by exp of x is also positive. So, this is positive. Just with this formula, this very nice relationship comes. So, if you notice here, exp of minus x is this guy. Okay, 1 minus x, it's got all sort of minus and plus and minus and plus. It turns out the negative terms are all smaller than the positive terms. Okay, so something like that has to happen so that this ends up being positive. Okay, that's another way to interpret this relationship. Okay, so this is exp of minus x is also greater than 0. So, what does that mean? X greater than 0, it's greater than 0. X less than 0, also it's greater than 0, right? So another way to interpret this, I'm sorry if we got that wrong. Exp of minus x is greater than 0 for x greater than 0. What does that mean? If x were to be negative, it's the same as saying exp of x is greater than 0 for x less than 0, right? Isn't it? So, I'm putting x equals minus x here, replace x with minus x, right? That's one way of thinking about it, but clearly this is the same thing, isn't it? These two are exactly equivalent, you know. For x greater than 0, exp of minus x is greater than 0. Instead of minus x, I'm going to say x here. So, I will have here minus x greater than 0, so it will be x less than 0 if you want to algebraically prove it, but clearly you can see these two are equivalent statements. Okay. So, what this means is exp of x as a function is positive for all x. Okay. Even if x goes negative, the positive terms here are greater than the negative terms, and exp of x becomes positive even if x is negative. Okay, so that's a very nice important fact to remember, and we proved it very easily using this inverse version, which is actually same as the addition formula. Look at the addition formula, right? The addition formula is behind all these properties. Okay, so very, very crucial and to understand. So, same thing you can push here. Exp of minus x will tend to 0 as x tends to infinity, right? What is exp of minus x is 1 by exp of x. As x tends to infinity, 1 by exp of x tends to infinity, so 1 by that will tend to 0. Okay, so exp of minus x tends to 0 as x tends to infinity. This is the other very nice property. So, exp of minus x, so when x is negative, exp of minus x, it starts at 0 and it's always positive and it's always increasing. We'll see that also, right? So, exp of minus y is less than exp of minus x for minus y less than minus x less than 0. So, this is sort of the property of this, the increasing property. We saw it for the positive values. For negative values also, if minus x is greater than minus y, then exp of minus x is greater than exp of minus y. This also follows from the inverse formula. Okay. So, think about why that should be true. I have exp of minus x times exp of minus exp of x times exp of minus x is equal to exp of y times exp of minus y. So, if exp of y is greater than exp of x, exp of minus x will be greater than exp of minus y. Okay, so that's the way to prove this. It's a very direct proof using the inverse formula. So, if minus x is greater than minus y on the negative line, if you go to the right, then the exponential function increases. Okay. So, exp of x is increasing for all x, it is positive for all x, and it starts at 0 and goes off to infinity. Okay. At 0 it becomes 1, at 1 it is e, and then it keeps on increasing. Okay, I hope this is clear. These properties are very easy and nice and intuitive, and all of them can be proven very easily. I hope you saw the proof of this. I just stated it in words. You can use exp of x times exp of minus x equals exp of y times exp of minus y. Once you see that equality, if this is exp of y is greater than exp of x, exp of minus x has to be greater than exp of minus y. So that's the way in which this proof goes. And all these properties are very useful in understanding the behavior of e power x. How does it behave with x? Okay. So now we can plot, right? So this is a plot. Desmos will give you this plot, but you can intuitively see this agrees with all the properties. It starts at 0, okay, at minus infinity, but even at minus 5 it looks pretty much like 0, okay. So it falls exponentially in the negative side and it rises exponentially on the positive side. So all the derivatives are positive, right? Derivatives are like rate of change, and all derivatives are the same and they're all positive. So it's sort of they reinforce each other, and it's sort of in a small change will get blown up in a big way. You can imagine this Taylor series type expansion, right? All the derivatives are equal and they're all the same value, and x and x squared, and as you keep deviating from a particular x naught, you'll just blow up in a very big way. It's monotonically increasing, right? So that also you can prove. What is the derivative of exp of x? It's exp of x itself, which is positive for all x. So the derivative is also positive and it's monotonically increasing. Because of the monotonically increasing nature, we have seen the inverse of a function, right? Any monotonic function is invertible. So the inverse of e power x is called the logarithm function. Okay, we won't see logarithm function immediately. We'll see it a little bit later. But this is also a very important special function, okay, as important as the exponential function. Okay, so the exponential function looks like this. Okay, just remember the shape. Notice the shape. Okay, notice some salient aspects of the shape. At 0 it is 1, at 1 it is e. Then look at the way it is blowing up. At 5 I can't even draw it very easily inside this. At 5 it is 2 point. I mean it's like it will go off to more than 30, 40 types. It looks like 40, 50 maybe, right? It's blowing up very, very, very quickly. Okay, so we'll characterize that also soon enough. So this is the exponential function, and this concludes this part of the lecture, which introduces the exponential function. We'll see more properties as we go along. Thank you.